Creo que podemos empezar también.
Okay, todo okay. Go ahead.
Sí. So let's start. Moment. Well, good morning, everyone, and welcome to our IPARCOS-UCM. Today, I'm pleased to introduce Dr. Carlos López-Coba. Carlos obtained his PhD at the Universidad Nacional Autónoma de Mexico in 2021 under the supervision of Sebastián Francisco Sánchez, who is the PI from the CALIPA survey. Afterwards, Carlos moved to Taipei in Taiwan, where he is currently working at the Academia Sinica Institute of Astronomy and Astrophysics as a distinguished postdoc fellow. His main research interests are focused on the dynamical processes of galaxies and their relation with star formation processes. He is an expert in the analysis of integral field spectroscopic data. Most of his work has been performed using large integral field spectroscopy galaxy surveys such as CALIPA, MANGA, and MUSE. Most recently, he has been also involved in analysis of the FANGS-MUSE dataset. He's also an expert in the kinematic modeling of galaxies. Particularly, he's interested in the modeling of non-axisymmetric flows. He's interested in the measuring radial flows induced by the largest structural components of galaxies, such as spiral arms and stellar bars. Today, Carlos will talk about exploring the imprints of non-axisymmetric motion in these galaxies, the case of NGC 1087, a bar galaxy or gas with an inflow motion. Thank you very much, Carlos. The floor is yours.
Thank you so much for to the organizer for letting me the chance of presenting my work in this seminar. So I prepared this seminar thinking about the students might be present, so there are some basic concepts in this talk that for the experts might be a little bit boring. Okay, so I'm going to talk about non-axisymmetric motions in galaxies, in particular, the case of NGC 1087, an special galaxy, which is a galaxy whether we don't know if it hosts a bar or the kinematics that we are observing is due to some sort of inflow motions or bar-like motions. I will explain in the following slides. So first of all, the non-axisymmetry in these galaxies, basically most of these galaxies in the universe show non-axisymmetric structures such as spiral arms, stellar bars. As I show in the right figure images, we observe clear a bar galaxy with two beautiful spiral arms, and the right side we observe a spiral galaxy with also beautiful spiral structure, right? So non-axisymmetry is basically ubiquitous in most of these galaxies. And if the gas and the particles within a galaxy rotate in the potential of an axisymmetrical dark halo, then it is expected that the axisymmetric it is expected that the particles or the bulk velocity of these particles follow circular orbits. For instance, in this plot, I showed what we would observe in a galaxy, in the galaxy plane. Basically, all particles or the bulk velocity of the particles following circular rotation around kinematic center, right? However, we only are able to measure the line of sight velocity of these particles. When we project these velocities along the line of sight, we will observe the left side velocity field. And this would be the case for a pure axisymmetric disk without spiral structure, without bars, without any non-axisymmetric structure. So this would be the velocity field that we would observe. We observe clearly approaching and receding sides, to half approaching and receding sides. In blue is the approaching and ready receding. And basically the kinematic position angle of the major kinematic position angle and the minor kinematic position angle of the galaxy are basically perpendicular to each other. So this model can be described by this simple equation in which BT represents the tangential velocity, or the so-called circular velocity is the inclination angle, and theta is an angle that depends on the kinematic center, position angle, inclination as well. If we compare the axisymmetric velocity field for an ideal galaxy without any non-axisymmetric perturbation, and for instance, we compare it with a typical velocity field of a disk galaxy, we observe that they are pretty similar. So in general, we observe that galaxies, most of the rotation is dominated by an axisymmetric component. And we can recover from this velocity map the so-called rotational curve, right? For instance, in the y-axis, we observe velocity, and the x-axis, we observe the galactocentric distance, and the points represent basically the different velocity, the velocity at different galactocentric radius. And we know that the maximum velocity can be parameterized. Sorry, the maximum velocity depends on the stellar mass of the galaxies. In the case of circular rotation, we know pretty well more or less the range of the circular rotation in galaxies. For instance, we know that for the most massive galaxies, the maximum velocity goes up to around 350 kilometers per second. And for the less massive galaxies, it can be up to 50 kilometers per second. However, we don't know how the non-axisymmetric velocities behaves in galaxies, because they can be quite complex. So in the presence of non-axisymmetric perturbation on the gravitational potential, we would expect that such non-axisymmetric perturbation also follow were coupled with non-axisymmetric velocities as well. For instance, in the case of this equation, which relates the unperturbed and perturbed gravitational potential, we expect that the red one, which is the unperturbed, follows basically circular rotation orbits, and the one that is the perturbed component will follow some kind of non-circular rotation. For instance, the most common examples of non-circular motions induced by non-axisymmetric perturbations are due to spiral arms, bars, bulge, as I mentioned before. Therefore, the line of sight velocity of a galaxy should contain both components, the axisymmetric part and the non-axisymmetric counterpart. Here I show two examples of two different galaxies from the MANGA survey. These are the main characteristics of this survey. This is an integral phase spectroscopy galaxy survey at spatial resolution of the order of 2.5 arc seconds, and which translates to physical scales of the order of kiloparsecs. So in the left panels, I show you the continuum image. This is the line of sight velocity traced with H alpha, basically the velocity field of H alpha, the model, the circular rotation model, and here I show you the residuals, which is basically subtract the line of sight velocity to the model, right? In all cases, we observe large non-circular rotation patterns in these galaxies. This can be due to many different sources, not only the non-axisymmetric ones, like I said before, bars, spiral arms, etc. But it could contain turbulence, it could contain galactic winds, it can contain many different sources of non-circular motions. If we take the residual map, we can make a quick study about the residual velocities. For instance, we can create a cumulative distribution of residuals in each case, right? So this should be A, not C. For the A case, this is the residual distributions. As you observe, we have both positive and negative values, right? And this is the cumulative distribution function. So as a way to parameterize the amount of non-circular motions, we can take the width of this distribution. For instance, W80, which is defined as the velocity at the 90th percentile, and the velocity minus the velocity at the 10th percentile. So this weight can give us some sort of insight about the degree of non-circular motions contained within a galaxy. Remember that for an axisymmetric disk, these W80 parameters should lie around 0 kilometers per second if all particles follow circular orbits, right? But we observe that this is not the case in general. For instance, for this galaxy, W80 is 50 kilometers per second, and for the other one is 30 kilometers per second. So we observe a large presence of non-circular motions in galaxies. At a higher resolution, this is observed in these two galaxies. These are from the Fangs-Muse survey. Here I show you the continuum image and also the emission line image traced with nitrogen 2, H alpha, and oxygen 3. And in the bottom panels, I show you the stellar velocity, the H alpha velocity, the corresponding circular rotation models, right? And in the bottom of panels, I show you the residual velocities, basically just subtract the observed minus the model. And we observe also large patterns of non-circular rotation. So if we estimated correctly the circular rotation, then all the residual velocities that we measure are deviation from circular rotation, indeed. So this means that these residual velocities, which goes between minus 30 to 30 kilometers per second, cannot be described with pure circular rotation models. So if we take the absolute value of these velocities, we would observe the large presence of non-circular rotation, for instance, in this galaxy. And here I have taken the advantage of using topographic techniques to enhance the continuum level, the continuum distribution of this galaxy. You can clearly observe that there are large scale non-circular rotation associated to the spiral structure and also to the inter-arm regions of the galaxy. The same happens with the right panels. We observed large scale residuals both in the stellar velocity and also in the ionized gas velocity. So in the particular case of bars, bars behave similarly. The ionized gas velocity behaves similarly in bars. For instance, here I show you 3 different cases of bar galaxies observed with Manga, Khalifa, and Muse. So basically, I am showing you galaxies with different spatial resolution, spectral resolution, etc. So again, I show you the line of sight velocity, the H alpha line of sight velocity in the left, the model in the middle, and the residual velocities at the right. And in all these cases, you observe this kind of this central distortion, right? It is better appreciated in the H alpha velocity. There is some sort of central distortion in the inner region where the bar is located. This is a signature of bars in the H alpha velocity field of galaxies. When we subtract the model, we observe these large blue shifted and redshifted components associated to the bar. So basically what is this telling us is that if we want to reproduce the line of sight velocities of bar galaxies, we cannot adopt simple circular rotation models, which is described by this equation. But the simple circular rotation models includes a large degree of a large number of free parameters. As I mentioned before, this depends on the kinematic center, inclination angle, position angle, systemic velocity, and all the different velocities associated to the rotational curve. So we must to develop tools for extracting the different velocities in galaxies. I mean, we must develop tools to extract in the most efficient way the different rotational components of galaxies if we want to estimate the non-circular rotation in galaxies. For this purpose, I have developed this tool, which is XS, which the main idea of this tool is to recover the non-circular rotation of galaxies, but it also recovers the circular rotation as well. And for this purpose, it adopts Bayesian inference methods. For those that are a bit involved with the Bayesian methods, you might know that there are two different ways or more for estimating the posterior distribution of the different parameters. For instance, by adopting MCMC methods or by adopting nested sampling methods. I will not go into detail, but for this work, I will adopt nested sampling methods, which basically do not depend on the initial conditions of the parameters. I mean, you don't need to know what is the inclination angle, the position angle, or the or the price for the different velocities components, since the nested sampling methods integrates over the whole parameter space of the different free parameters. This is much better than MCMC's method, but it takes more time for computing this integral. And this has been applied to different circular and non-circular rotation models. For instance, the classical circular rotation model that I showed you before, radial flow models, and bisymmetric models, and an arbitrary harmonic decomposition. These 3-4 non-axisymmetric flow models are the most adopted in the literature. The bisymmetric model was developed by Christine Spickens and Selwood, 2007, and the harmonic expansion was introduced first in Schoenmakers et al. 1997. And just to give you an example, this is the results applied for a bar galaxy using the XS tool. And here in the left, I show you the marginalization over 40 different parameters describing the non-circular rotation in a bar galaxy. This is basically the circular rotation. All these are the different velocities. These are the non-circular rotation. Where is this one? B2T and B2R are basically the tangential and the radial velocities induced by the bar. And this is the disk geometry of the galaxy. So this is just an example of what this tool can do. And we can apply these tools for describing the line of sight velocity of bar galaxies. For instance, in this case, this is a bar galaxy from Muse. We observe a clear bar in the optical images. And also we observe the central distortion, right, in the H-alpha velocity field. After modeling this galaxy with a bisymmetric model, which takes into account the radial and tangential velocities induced by the bar, we are able to reproduce the inner distortion, and the residual velocities are the residual velocities do not exhibit such a large blue shifted and reshifted component, which means that this is a great success for modeling this velocity field. But in a similar way, we can model a bar galaxy with a harmonic decomposition, assuming assuming an harmonic expansion for a second order perturbation, which would be this expression. So basically, both of these models try to simulate or try to replicate the line of sight velocity observed in barred galaxies. Now, why did I say all this before? Because we know that the velocity field of galaxies can be a very powerful tool for unveiling or for revealing the non-axisymmetry in galaxies. In all these cases, we know that these galaxies exhibit a stellar bar, and therefore we are able to perform different kinematic models that include non-circular rotation. But there could be cases in which a bar is not obvious in the optical and might contain some sort of non-circular motion associated to a bar-like structure. This is NGC 1087. This is a SV galaxy at 40 megaparsecs. This is a galaxy from the nearby universe. And here in the left figure, I show you the continuum image constructed with the GRA bands from the Muse data cube. So if you observe the central region, there is no evidence of a stellar bar, or at least there is not, this galaxy do not exhibit a classical stellar bar, a large bar, right, in which is evident, it is evident along a long bar towards a defined position angle. So this galaxy is very dusty in the central region. We even detect some very bright spots, but there is no any clue that this galaxy might host a stellar bar. So this data was obtained from the Muse, from the FANGS Muse survey. All this data is public. You can go to the archive and download it and analyze by yourself. This is the full width and maximum spatial resolution, which is of the order of 60 parsecs at the distance of this object. And this galaxy was analyzed with the PyPipe 3D tool from LOSV et al. 2022. And this is basically some of the data products produced by this pipeline. All those involved in IFS studies know that this is one of the main data products of the different IFS tools. Here I show you the ionized gas distribution of this object again. In the central region, there is a conglomeration. It seems that there is a conglomeration of gas exhibiting some sort of alienation, but it is not even clear that this alienation might be due to a bar. In fact, if we analyze only the central region where might be possible, might be exist a bar, and we plot the BPT diagram, this is not the BPT diagram, one of the BPTs diagram, which involves the ratio of oxygen 3 and H beta, and in this case, oxygen 1, which is a good tracer of shocks over H alpha. We will notice that all the ionized gas within the bar region is compatible with star-forming ionization. And the shock models cannot explain the observed line ratios. Also, the equivalent width of H alpha has been adopted to identify, or is an auxiliary tool for identify the different ionization sources of galaxies. Basically, equivalent widths of H alpha larger than 6, or it depends, larger than 6 or larger than 3, are associated to star-forming regions, and those equivalent widths of H alpha lower than 3 Armstrong are basically associated to a diffuse component, for instance, ionized gas by all stars, by post-AGB stars, by dwarf stars, for instance. In the case of this galaxy, all the ionized gas in the bar regions seems to be associated to star-forming processes. Combined with public ALMA data, also from the FANGS ALMA data, also published in Leroy et al. 2021, we can trace the molecular gas density across this galaxy, in particular in the central region. And we observe an enhancement of the CO line intensity in the central region. This is the full width hat maximum resolution for this object of the order of 110 parsec, right? And finally, combine this data with the JWST image, in particular the F200W filter, which basically traces mostly stellar continuum, the infrared, right? We observe that there is a conglomeration of continuum emission in the central region, and all this emission seems to be elongated towards a preferred position angle. So if we perform some isophoton analysis only in the central region of this object, we would observe that the isophones are aligned along this position angle, 305, which differs from the global orientation of the galaxy, which is around 1 degree, between 1 and -1 degree. So the spatial resolution at the distance of this object from JWST is of the order of 3 parsec, and we are able to observe individual globular clusters in this galaxy. So if we perform a more robust analysis trying to model the central region of this object using the F200 and W filter and 300 and M, both of these filters trace basically a stellar continuum. We observe that the central emission, the central infrared emission, can be modeled with a exponential disk with a constant position angle in 305 and a constant ellipticity of 0.5. This is the model and this is the residual. Okay, and finally, thanks to the intergalactic spectroscopy data provided from MUSE, we are also able to trace the stellar kinematics of this object. So we are able to trace the CO velocity, the H alpha velocity, and the stellar velocity for this object. And here I observed the 3 line of sight velocities and assume around the bar-like structures, which is around 30 arc seconds times 20 arc seconds. So in all these cases, we observe a central distortion in CO, H alpha, and also in the stellar velocity. The black line represents the position angle of the infrared light observed by the JWST, right? In all these cases, we observe some sort of distortion, probably associated to the bar, to the infrared bar observed. In fact, if we overlay the CO isovelocity contours in the JWST image, we would observe that the isovelocity lines are aligned parallel to the bar, to the infrared bar. But this has been observed before in H1 data, and since 1984 we know that how gas behaves in the presence of bar-like distortion. So here I show you a cartoon of basically the velocity, how the velocity field of a barred galaxy behaves in the presence of a bar. Basically, all the isovelocities tend to align along the bar position angle, or along the bar position angle, right? And this is clearly observed in these cases. There is some sort of distortion that might be associated to the bar, and all these isovelocities are sort of aligned to the bar position angle. So if we perform a circular rotation model in all these three velocity maps and we subtract it to the observed one, we would obtain the residual velocities, which is observed here. In all these cases, we observe large sources of non-circular motions of the order of 30 kilometers per second, right? So this is basically telling us that the velocity field in the inner region of this galaxy cannot be described by pure circular rotation due to the large circular velocities that we are observing. And these blue shifted and redshifted patterns are observed simultaneously in the stellar H alpha and molecular gas. That is, the bar potential or the bar distortion is observed simultaneously in three different phases: molecular, ionized, and stellar velocity. And here I show you the circular rotation obtained with the XS tool. More or less, the three rotational curves share the same profile with the most common adopted non-circular motion model is the one proposed by Christian Spickens in 2007, which intends to describe the elliptical orbits induced by the bar. So here on the left, I show you a cartoon of the gas velocity field in a barred galaxy. The velocity field in bars can be quite complex, and the hydrodynamical models predict that in the absence of bar dust lanes, the particle should follow quasi-elliptical orbits. And for these orbits, the bisymmetric model is a good model for recovering the tangential and the radial velocities. So as you observe in this equation, the bisymmetric model contains the circular rotation traced with the BT and two non-circular components, B2R and B2T. And the non-circular velocities depends on the position angle of the bar on the galaxy plane. So this model successfully described the observed velocity field in this galaxy. Here I show you the bisymmetric model applied to the molecular H alpha and the stellar velocity. In all these cases, we are able to reproduce the inner distortion just by fixing the position angle of the kinematic distortion at the position angle of the infrared bar. So the inner distortion is totally reproduced. So we might think that the main source of non-circular motions in this galaxy is due to a bar inducing bisymmetric flows, which is expected in the case of a bar. So far, the stellar velocity, the ionized gas, and the molecular gas velocities are compatible with the presence of a stellar bar, or are compatible with the presence of a bar-like perturbation in the potential. As I mentioned before, one of the flows that are expected to occur in bars are inflowings along the bar dust lanes. After the gas is shocked, after the gas reaches the bar dust lane, it shocks and loses angular momentum and infalls towards the galactic center. This inflow is expected as well in barred galaxies, but due to the complexity of these flows, are difficult to associate the non-circular motions observed to an inflowing gas. And in this paper in López-Coba in 2024, we developed a non-axisymmetric inflow model, which tries to take into account an inflow of gas along a fixed position angle. In this case, the bar position angle. So we have in this model the circular velocity and the radial velocity of the gas, which depends, as I mentioned before, on the bar position angle. After applying the inflow model, we observe that the inflow model is also able to reproduce the observed velocity field on the molecular gas and the ionized gas. And in yellow circles, I show you the root mean squared of the model. So this is highest for the circular rotation model, because it's basically telling us that we are not able to describe the non-circular motions with pure circular rotation. And the inflow model shows the lowest root mean square value. And not only show the lowest root mean square value, it also shows the lowest big value. So statistically speaking, the inflowing model is preferred over the bisymmetric model, which takes into account quasi-elliptical orbits. However, the real scenario is that it could be more complex than that. It could occur the two different it could happen the two different velocities at the same time. You can have gas falling quasi-elliptical orbits. You could have as well gas inflowing along the main bar axis, right? If we believe that the inflow gas model is the most dominant in this galaxy, then we are able to trace the inflow rate induced by the bar. So in the left panel, I show you the molecular inflow rate estimated with this expression, which depends on the molecular surface density and the inflow velocity. The inflow velocity is obtained from our kinematic modelings, which is observed here in orange, right? So this is basically the inflow velocity along the bar axis. So this inflow velocity goes from minus 20, so around minus 50 kilometers per second to 0 kilometers per second, right? This is the radial profile. And with this radial velocity, we're able to estimate the molecular inflow rate, which is observed here in gray colors. So the average mass inflow rate induced by this inflowing motion is of the order of 20 solar masses per year. And in the top panel, I show you the 2D the 2D maps associated to this mass inflow rate, because R is a 2D map, sigma is a 2D map, the inflow velocity is also a 2D map. So basically, we are able to construct a two-dimensional map of the inflow rate, molecular inflow rate. So the conclusion for this object is that the velocity field is quite complex. It can contain both quasi-elliptical orbits. It can contain also inflowing motions, but the inflowing motion seems to be the dominant non-circular motions in this galaxy. The inflow motion associated is able to reproduce the observed star formation rate of 0.1 solar masses per year. This means that at this average inflow rate, the molecular gas is piling up in the central region and therefore is fueling the central star formation that we are observing in this galaxy. And here I just want to leave my slides of remarks in conclusion, and I want to say that non-circular motions are quite important in galaxies, and if we want to study the influence of non-circular motion in galaxies, we need to create, or we need to develop tools for analyzing non-circular motions. This basically means that we need to develop models for trying to recover the non-circular rotation of galaxies. And in this case, in this galaxy, we observe that the large source of non-circular motions can be both described by a bar-like flow or also by an inflowing motion. So even though that the optical continuum image do not exhibit a stellar bar, a clear stellar bar, the kinematic shows that there is something there. And in particular, such distortion observed in the molecular ionized gas and stellar velocity are compatible simultaneously with a bisymmetric model and an inflowing model. So which is the most dominant? It's not straightforward. At least the results suggest that the inflowing model is the most dominant motion. And if you observe an inflowing gas, and you observe also that the infrared image from JWST shows an elongated structure, probably associated to a stellar bar, we might conclude that the non-circular motions in this galaxy are associated to a near-infrared bar, although it's not optically detected. That's pretty much. Thank you so much.
Thank you very much, Carlos. Very interesting talk. So time for questions. Patricia, go ahead. We cannot hear you.
Sorry.
No,
No, I was saying that thank you very much, Carl, for the talk. I enjoyed it a lot. And also to you, Enrica, that I have a lot of questions, so just stop me when you...
No, don't worry.
Okay, first of all, I mean, I would like to know more details about your tool for developing the kinematical models. I mean, the difference with the standard, I don't know, with the harmonic expansion, things like that, is the way it minimizes the line of sight velocity, or is or there is something else that is conceptual that is that I'm missing?
No, basically it's the same. It's the same. It's the same that
It's just the way
reduces.
it minimizes, no? So instead of just where a chi-square, it does some
Yeah. Basically, yeah.
Okay, thank you.
The input is a velocity.
Okay, thank you.
Field.
Are you always assuming like an infinitely thin disk, or are you having to account possible vertical motions?
If you want to, no, I don't. Yeah, I mean, yes, I assume that the disk is plane.
Okay.
Right. If you do not assume that, so if you assume that the disk, the position angle and the inclination angle have a radial dependence, this might add non-circular sources to the observed line of sight velocity that might be not real. So if you want to enhance the detection of non-circular motions, you better assume that the disk is flat.
Yeah, no, I mean, I agree with that, but also not assuming it, and if there is, I mean, if the disk is not completely thin, no, and for example, if your tracer, I don't know, you can maybe compare your results using the CO and the ionized gas, which is a little bit hotter, and see the difference. But also the vertical motions can introduce artificial non-circular motions, even if they are not circular motions, no, in the model. So that's what I'm asking.
Yeah, that's right.
And related with this, well, I'm going to ask Mercedes a question as well, but related with this, in your conclusions, I was wondering if you can actually separate the two possible sources of these non-circular motions, the fact that you have an oval,
quasi-elliptical orbits
or radial flows, comparing, in fact, the stellar kinematics with the molecular or the ionized gas. I don't know if you've done this exercise. Because you don't expect that the gas produce flows in the stars, no, like in the gas, I guess, by torque.
Yeah. That's why this was not considered. The inflowing model was just considered for the gas, for the molecular and the ionized gas, not for the stellar velocity.
Agree, but
So
if you apply I mean, if you can apply the same for the stars to see if you get results that are compatible with inflow despite you don't expect it. I mean, it's like a control test, no? Like what happens if you use a tracer where you will not expect like radial flow, or if you subtract what you expect by eccentric orbits, what do you get? I mean, what do you have left on the gas? No? I don't know. I was just wondering that because you have all the different tracers, you could actually compare them and see and learn something about learn something.
Yeah. I agree. I agree with you. We
We
didn't do this analysis for in this paper.
Okay, no, it's very interesting.
Certainly, it's quite
Okay,
interesting.
Merced Romero asked, actually I was going to say, but Merced Romero had to leave, Merced Romero Gomez, but he left a question that say that, I mean, what are the uncertainties introduced by uncertainties in the inclination and the position angle? No? That always, they always can introduce artificial non-circular motions as well. So what do you think?
Yeah, this is always the same question. So far, there are people that considers that might be variation in the inclination angle, in the position angle. But if the disks are flat, then you do not expect that.
I don't think he was meaning along the radius, but just in the position angle and in the inclination of the galaxy that is they are difficult to determine anyway.
Yeah, in fact, this is why we developed this tool. Because the idea of developing this tool is to have the most accurate measurement of the different kinematic components. And this does not assume, this assumes that all different parameters are independent. So the uncertainties on the different velocities also take into account the different variations in the inclination angle, position angle, etc. So basically the other tools that are in the literature, such as this fit, kinematry, etc., adopts least square methods. And a little bit of the idea of this tool is doing like some sort of the similar analysis, but trying to emphasize or put an emphasis in the uncertainties in the different velocities. I agree. Uncertainties are quite complex, quite complex, and they are difficult to quantify. So far, this is our best approach in estimating the non-circular, the uncertainties, and we have tested our tool with the most used ones in the literature, and basically they have the same order. So Bayesian methods and the least square methods produce the same order of the same amplitude order of errors.
Okay. I will modify and I will stop. I will leave other people out. Is it public the software of the tool?
Yeah. Okay. Where is did I put here is the GitHub page.
Okay. Thank you very much, Carlos. I enjoyed a lot your talk, and I will shut up now. So other people
Thank you so much.
Thank you.
Thank you, Carlos. Well, other question? I have one question, and I was wondering, you just shown the velocity field of the ionized molecular and stellar emission. Did you apply your model also to the velocity dispersion? Do you see any difference between the velocity dispersion of the ionized or molecular and stellar maps?
I don't show the velocity dispersion, but certainly the velocity dispersion is enhanced in the bar region. So these two are coupled. For the because for extracting the for performing the models at this stage, we don't need the velocity dispersion map. We don't use it, and we didn't want to present it in the paper as well. But certainly there is the dispersion is increased in the CO in the molecular phase that in the ionized gas phases. Yeah.
Wouldn't be useful to distinguish between bar and inflow structure?
Somehow I don't have clear how it could be applied at this moment. Yeah, I need to work on that. Yeah.
Okay. And another quick question. And did you try to apply multi-component fitting to the ionized? Did you see asymmetric profile in the ionized emission gas?
That we didn't do that analysis because first of all, in this work we want to use the data products directly from the pipeline, and so far this is not one of the data products. And second, because there are many spaxels.
Okay. Yes.
Yeah. So making this analysis to one Fangs galaxy, do you know Fangs,
Yes.
the Fangs galaxy, right?
Yes.
So there are millions of the individual spaxels in just one observation. So it will take ages for us to do this analysis. If the code is not parallelized, so it will take several days to do that analysis. No.
Okay.
We avoid doing that analysis, but it would be really interesting. So because shocks are expected along the bar, and it is expected that if there are shocks, you should observe multiple components along the bar structure. That would be an indicator of shocks. So that would be an indicator that the gas is indeed inflowing along the bar structure. And this would support the idea of the inflowing motions over the bisymmetric model, which takes into account the quasi-elliptical orbits. Yeah, but we didn't do that in this work.
Well,
because
for
we
the
don't
next
have
one.
the tools for doing that, basically.
Yes,
Yeah,
well,
maybe next time.
the next one, next work.
Yeah,
So,
sure.
I think we can stop here. Thank you very much, Carlos, again. We enjoyed a lot your talk. So thank you very much to everyone for joining us.
Thank you so much for the invitation.
Thank you.